Hello everybody, thank you for waiting. My name's Emma and I'm here to facilitate today's event. I hope you're all well and safe. This session today will be on the topic of sequences and series. I'm one of the WP officers here at the university, so if you have any questions, just give us a shout. Today I'm joined by Dr. Rhian Taylor, who's one of our lecturers in mathematics, and she'll be running today's revision session. Hi Rhian.
Hello, are you okay?
Yes, thank you. So she'll pop up shortly. I'll hand over to her in a sec, but during the presentation, you'll be given the opportunity to ask questions in the chat function on the right-hand side of your screen. Your audio and video won't be shared, but you can ask questions anonymously if you wish. You just need to have tick the box to say you wish to remain anonymous. You can like other people's questions if you want to, just to indicate your interest, and I'll collate these questions and ask Rhian at the end of the session. Okay, so we're ready to start. I'm going to hand you over to Rhian and I hope you enjoy your session.
Perfect. Thank you for that, Emma. So in this session, I just wanted to go over two things, so arithmetic series and geometric series. I've got quite a good range of questions to go through and then some quite difficult, harder exam style questions at the end. But what I wanted to start with was just a nice definition and formula. You should have access to these notes as well if you wanted to go through this while we're working through it. Or I'll upload the full notes after the session as well, and you can just look back at these. So one popular thing that you might get in any tests or assessments that you're doing this year is the sum of the first n terms, which I'm sure you've done quite a few times. So an arithmetic series is just adding up the same amount each time. So our first term is just a, our next term is a plus that difference, d, the third term is a plus 2d, and so on. So if we want the sum of the first n terms, we'll go for Sn. So I'll go for the first term and then add each term up after that, and we want to make a nice formula for this. So we've got a plus d will be our second term, a plus 2d will be our third term, and then I'll put some dots in between. The nth term of this sequence will go up to a plus n minus 1d. So if I add in the last two terms there, we've got a plus n minus 2d and then a plus n minus 1d at the end. So that's the sum of our whole sequence. If you get this in any exam style questions, any assessment questions, it's usually in the form of prove that the sum of the first n terms is this. So you'll be given this final line. So we've got n over 2 times 2a plus n minus 1d. So we know that that is what we want to prove. It definitely helps with any proof. Just write down, leave a few lines and write down what you're trying to get to, because then you've always got that in your mind and you're always trying to get to that at the end. An easy thing to do from that step is if I just move that 2 divided by 2 at the end, 2 times by 2 there, this sequence looks a bit nicer, and that's exactly how we want to approach that proof. So we want to calculate 2 times this sum. So all you want to do is write out that sum again, and then we'll add these up, and that'll be 2 of those sums, and hopefully we'll get this n times 2a plus n minus 1d. The only trick that you've got to remember with this one, it just makes it easier, is if you write it backwards. So if we write the exact same thing, but I'll start with the last term, and then I'll go with the second to last term, and so on. Then our last 2 terms at the end, a plus d and a. And if you wrote this in any test, this is all 3 or 4 marks, depending on which exam board you're with, and that's all we've got to do for it. So if we added up these both these two rows, we've got A on the top, A plus n minus 1d. We get 2A plus n minus 1d, and we get that for each of those as we add them down. In the whole sequence, we've got n of them all together, so that's where our n comes from. So we've got n times 2A plus n minus 1d. And that was our two sums added together. So if we just divide that by 2, we've got our final line. And it's a nice, easy proof to remember. So we'll go on to some practice questions. That's still there. The first one is for the third and the eighth term of an arithmetic series is 72 and 37. So what we have there we go. Each term of the sequence is defined as A plus n minus 1 times d. So I'll write that out for each one. For our first one, our third term will be A plus, when n is 3, it'll be A plus 2d, and that third term was 72. For the eighth term, we've got A plus 7d, and that term is 37. So a lot of these questions you'll realise are just simultaneous equations. I'll give you some time to start that one. Just working out your simultaneous equations so that you find the first term, which is our A, and the common difference, which is D. The easiest thing to do with them would probably to be switch them around, take them away from each other, and you'll get your A and your D for that one. So if you take them away, you get 5D equals minus 35, which gives D is minus 7. And then we can sub that back in to find our value for A. And you should get A is 86 from that. So that was quite a nice question to start with. The questions that usually follow that are find the sum of the first however many terms of the series. So we'll use the formula that we proved at the top. And we'll just put all of our values in for A, N, and D. So if we have A is 86, D is minus 7, and N, we want to find the sum of the first 25 terms, so our N is 25. And all of that we're just going to put into our formula. You'll get this one on your formula booklet, and in any assessment that you do, you should still have your formula booklet with you. So we have the first 25 terms, n over 2 times 2 times A plus n minus 1 times D. And that's just a nice calculation, but nice mark. So I'll let you go through this one. At the end, we'll upload all the full solutions for you as well. So I'll leave you to do that one. So those two were quite nice to start with, but I wanted to look at some different styles of questions. So the next one that I want to do is just worded slightly differently. So we've got the sum of the first 6 terms of the series is 213, and the sum of the first 10 terms of the series is 295. So we just want to find, again, the first term and the common difference. So it's similar to the last one in that it's probably still simultaneous equations, but it's not in the exact same layout that we had before. So if we use the same formula for the sum of the first 6 terms, that was my n over 2 times 2a plus n minus 1d. So when n is 6, it'll be 5d. the sum of the first 6 terms was 213. So that's our first equation. The sum of the first 10 terms of the series is 295. So when n is 10, n over 2 times 2a plus n minus 1 will be 9d. That sum is 295. And again, we've just got some nice simultaneous equations here. The first one, 6 over 2, is all times by 3. And the bottom equation, 10 over 2, is all times by 5. The 213 looks like it divides by 3 as well, and the 295 looks like it divides by 5. So to rearrange it and make it a bit nicer, I'll divide this top one by 3. So I'll get 2a plus 5d, 213 divided by 3, 71. There are loads of ways to do these simultaneous equations, so you don't have to stick to this one. I just go for the easiest, probably laziest method. 10 over 2 from the next one, so that's all times by 5, so I'll divide both sides by 5, and I get 2a plus 9d is 59. And then we've got 2a for both of them, so for those equations we can just take them away from each other. A lot of these are just simultaneous equations practice. So 5d minus 9d minus 4d equals 12. So then we should get d is minus 3. That was most of the work, and then we'll just sub that back in to either equation to find our value of a then. So if I just go to that nice equation that we made of 2a plus 5d equals 71, and sub in d is minus 3. I think we get 2a is 86, and then we'll have a is 43. So it's a lot of simultaneous equations practice. The next one that I'll go on to, so we'll use those values that we have, and this one gets a little bit trickier. So the part B, find the number of positive terms in the series. So the common difference between each term was minus 3. So this series is getting smaller each time. So we had, I'll just remind myself at the top, A is 43, D is minus 3. So because we want the number of positive terms in the series, we want the greatest number for n, so that a plus n minus 1 times d is still a positive number, because then after that they'll start going negative. So we just want to solve this for the greatest number of n. So if our first term was 43, our common difference is minus 3, and then that's a nice inequality just to solve for n. So from that we should get n is less than 46 over 3, the greatest number that n could be. If it's less than 46 over 3, which is about 15 and a third, the greatest number that n could be is then 15. So there must be 15 positive terms in this series, and then after that the 16th term would be negative. This follows on nicely to the next question, which is hence find the maximum value of Sn. If you ever have a hence question, make sure you're using what you've done before. It just makes it much easier for you. So we want the sum of the first n terms of that series. So if we use our n is 15, our a and d as before, then it's just subbing everything into our equation again. So we'll have n over 2 times 2a plus n minus 1d. And if you sub in everything that you've got from there, I'll give you some time to do that one. I think for that one, you should get about 330 if you sub in A is 43, D is -3, and N is 15. You can check that if you do the sum to n terms of the first 14 terms and then sum to n terms of the first 16 terms and see if that sum of your 15 terms is the maximum. So you should get 330 for that one. The next one that I wanted to look at is more of an algebraic one. So this one looks at the 5th, 6th and 7th term of an arithmetic series. And we just want to find the value of the constant t. So if we know that this is the 5th term, that in terms of our a and d would be a plus 4d, and then we'd have a plus 5d, and then a plus 6d will be our 7th term. We would have there 3 equations and 3 unknowns, and we can calculate what our a, d and t are. But there's a slightly easier way to do this one. So if we know that these are 3 consecutive terms from the 5th, 6th and 7th term, then we know that the difference between each of them is the same. So they're just adding the same amount on each time. So if I done the middle term, got 2t, and take away the first term, I'd be left with just the difference between those 2 terms. So that would be the same as doing the final term, 6t minus 3, take away that middle term, take away 2t. And then we've just got one equation in t to solve, which is much nicer. So I think you get 3t minus 5 and then 4t minus 3. And that works out really nice for t is -2. What's nice to do from that is just sub it back in to what we had. So 5 minus t would be 7, 2t would be -4, and 6t minus 3 would be -15. So that's our 5th, 6th and 7th term of our series. The next part we want to do for part B is find the sum of the first 18 terms of the series. So we're going to use our formula again, where our n equals 18, but in this one we need our a, our first term, and d, the common difference between each term. So we can see that from the 5th, 6th and 7th terms that we've got 7, -4 and -15, the common difference between each term is just going down in 11, so it's -11. And then we just need to work out what our first term would have been. You can kind of work backwards, write it out in a sequence. I know some people would like to just add on the 11s and work backwards from your 5th, 6th and 7th term. But if you know the 5th term, a plus 4d equals 7, and we know that d is -11, then we can use that to work out our value of a. So that should be 44 plus 7, and that will be 51. So we get our first term of 51. We know our common difference, and we know what n. We want the sum of the first 18 terms, so n is 18. So we'll put all of that into our formula again. N over 2 times 2a plus n minus 1 times d. And I'll give you some time to work out all of that one too. We know that from the fifth term was 7, sixth term was -4, seventh term was -15. This is going to get a lot of negative values in the sequence. So up to the 18 terms, we'd expect quite a high negative number. And I think for that one, you should get -765. I found one more. I only wanted to do one algebraic one in this, but I found another more horrible algebraic one. So I threw this one in as well. So if we look at our final algebraic question for this, and then I'll go on to geometric series as well. We've got the first 3 terms of an arithmetic series are k plus 4, 4k minus 2, and k squared minus 2. And then we've got something which looks completely unrelated, show that k squared minus 7k plus 6 equals 0. So really similar to the last question on how we looked at the difference between each one. We know that these are the first 3 terms, so we know that they're consecutive terms. So if I do the final term, k squared minus 2, take away the term before that, 4k minus 2, that'll give me my difference between those terms, which would be the same as the difference between the first and the second term. So that's 4k minus 2, and then minus k plus 4. So hopefully, if I expand all of this, get it all onto one side, I'll get that k squared minus 7k plus 6 equals 0. That one should work out quite nicely. But we have a second part to that question, which is, given also that the common difference of the series is positive, find the 15th term of the series. So if we wanted the 15th term, that would just be a plus n minus 1d, where n is 15. So that would just be a plus 14d. So first of all, we need to solve this for k so that we know and we can work out our common difference between them then. So if we just factorise our k squared minus 7k plus 6, you can probably just do this on your calculators. I hope that you all still think about these. Don't automatically go straight to your calculators. We'll get 2 solutions, so either k is 6 or k is 1. If we look at these 2 solutions, if k is 1, then our first term of the series would be 5, our second term would be 2, and our third term would be minus 1. However, if k is 6, then my first term of the series would be 10. My second term, if I sub that in, will be 22. And my third term there will be 34. So given that the common difference of the series is positive, so this series is increasing, then we want to find the 15th term. So we'd know that we have to use our k equals 6 for this one. And we've got our first 3 terms, 10, 12, and 34. So if I go on to that last part of the question, we'll just sub in those values. So my first term, A, was just 10. My common difference between each term, you can work out, is just 12 between each one. And then if we sub all of those in, we'll get our 15th term, which is quite a nice one to do. So we have a plus n minus 1d, where we have 10 plus 15 minus 1 times the common difference between them, which is 12. And for that one, I think you should get 178 as the 15th term there. So if we're happy with the arithmetic series, I'll go on to geometric ones, and then I've got some really horrible questions at the end, which combine them a lot in exam style questions as well. So the geometric, really similar to the arithmetic, all we've got now is the common ratio instead of the common difference. So it's just being times by the same amount each time. So we'll again start with our first term of a. Then our next term will be a times r. Each time we're going to times that by r. So then we'll have a times r, which will be ar squared, and then ar cubed, and so on. So first of all, I want to go through the sum of the first n terms. So if we try and write out exactly like we did with the last one, our sum of those terms, we'll have a, and then plus the second term, ar, plus the third term, ar squared, and then I'll keep going up to the nth term. I'll do the last two terms there. So I'll have ar to the n minus 2, and then finally ar to the n minus 1. Because we just want to prove the sum to be this formula, you'd be given this in order to prove it. And if we rearrange this, we can see how you need to approach this proof. So if I just take off that 1 minus r from the bottom, I'll have 1 minus r times fn equals a times 1 minus r to the n. And if I expand that left-hand side, that's just Sn minus Rsn. I'll expand the right. We've just got A minus AR to the n. So this is how we want to approach it. We want to work with this Sn, and we'll just take away R times Sn. So if on my next line I calculate R times Sn, and then I'll just take these away, hopefully I'll get A minus AR to the n at the end. So if I do R times my sum, I'll just add another R to each of these. So I've got AR plus AR squared plus AR cubed up to AR to the n minus 1, and then finally AR to the n at the end. And I just want to take away both of these. So if I do Sn minus R Sn, I'll factorise that out already. A lot of these terms will cancel, so my ARs should go there. These will match up, so I'll get rid of those two terms, those two, AR cubes will go, and so on. And I'm not actually left with much, I'm only left with the first term A, and then in my second line, I'm only left with AR to the n. And then if I factor out my A from there, I've got my A times 1 minus R to the n. So if you always start with the final line as well of what you want to achieve, kind of work backwards from there, it just helps keep you on track too. So it's a nice proof of just 4 lines, just for 4 marks. The interesting thing with this sum is that you could be asked for then the sum to infinity. So this is only if the modulus of r is less than 1. So if the modulus of r is less than 1, we'll look at what happens to n as it gets bigger, as n gets closer to infinity. Where we have the n in this formula is in that r to the n. So r, if it's less than 1, if you've done a half to a really high power, that would just get smaller and smaller depending on which power that you've done. So as n gets bigger, r to the n will get smaller and closer to 0. So we want our limit as n gets larger would just be r to the n would get close to 0. So then I'd have 1 minus 0 in that top bracket, and I'd just be left with a over 1 minus r. So that's our formula if we want to use, if we're asked the sum to infinity, we'll use that formula as well. So we'll have a look at some questions that we've got. So I've started quite similar in these ones. The second and third terms of a geometric series are 2 and 10 respectively. So first of all, we want to find the common ratio of the series. And then the next part was find the first term of the series. So in terms of A and R, the second term would be AR, and that's 2. The third term in terms of A and R would be AR squared, and that would be 10. So we've got 2 equations with 2 unknowns. So again, we can do simultaneous equations on this. A lot of people like to rearrange this for A, sub it into something else. I think the easiest thing to do with these, because it's all working with ratios, is to divide them. So if we do AR squared divided by AR, so that would have been my 10 by 2. AR squared divided by AR just leaves you with an R, because your A's will cancel. You'll be left with 1R, and we'll be left with 5. So that was a nice one log. The R is 5. The next part that we'd have is just to find the first term of the series then. So if we know that the second term, AR, was 2, and from the first part, we've calculated that R was 5. And then it's quite a nice calculation to work out our first term, A. You can always check with these ones that they work. So if A is 2/5 and my common ratio is 5, it should be getting 5 times bigger each time. So I'll start with 2/5. My second term times that by 5 would be 2. My third term, if I times that by 5, would be 10. Fourth term, if I times that by 5, will be 50, and so on. So a lot of these get really big really quickly. So we're just going to look at the sum of the first 8 terms of the series. So these are usually quite big numbers, just for the sum of the first 8 terms. So we've already got 50 at our fourth term. It'd probably be quite easy to just write out your 8 terms as well, but we'll use our fancy formula, which is A times 1 minus R to the N all over 1 minus R. And we're just subbing in A is 2/5, R is 5, and N is 8. And I'll let you work that one out. So that 2/5, we started with 0.4, and then everything after that will be whole numbers. So we might end up with a 0.4 at the end of this, and it should be quite a big number. I think you get about 39,062.4. So if we look at a slightly different one for the wording of it, a lot of this is still simultaneous equations, but it's just forming those equations. So in our next question, we have the sum of the first 4 terms of a geometric series is 130, and we're given that the common ratio is 3/2. So we know that R is 1.5. So if we use our formula for the sum of the first 4 terms, that was A times 1 minus R, which we know is 3/2, to the power of N, which is 4, all over 1 minus R, 3/2. And we know that this equals 130. So we formed an equation from that first line, find the first term of the series. We've just got to rearrange all of this for A. This is quite a nice one to do, as horrible as it looks. So you can just move up what you've got on the bottom and rearrange everything for A. So we should have minus a half left on the bottom, so you can times that up by minus a half, and then divide by 1 minus 3 over 2 to the power of 4. I'll let you try that one, and I think you should get the answer of A is 16 for that. So that's our first term. We start with 16, and then we're timesing it by 3 over 2 each time. The next part that we have is to just find the 8th term of the series. So our 8th term in terms of A and R would just be A times R to the 7. So we've just got 16 times R was 3 over 2, and we'll raise that to the power of 7. So that's a nice calculation, which gives around 273. The part C for this one is definitely the worst. So find the least value of n for which the sum of the first n terms of the series is greater than 30,000. So we're looking at the sum of the first n terms, and we want this value to be greater than 30,000. So my formula for the sum of the first n terms would be A times 1 minus r to the n all over 1 minus r. And we want this to be greater than 30,000. So if we sub in what we know so far, so we know that A is 16, and we know that R is 3 over 2. And then we've just got to solve this for n. So usually people already don't like this one because what we've got to solve it for is a power. But if I just start to rearrange it, so the 1 minus 3 over 2 on the bottom is just minus a half. So if I do 16 divided by minus a half, that gives me minus 32. And I'll multiply out by this minus 32 and then start rearranging things. So I get minus 32 plus 32 times 3 over 2 to the power of n. There are a few ways that you can rearrange this, so you can try a few. And then I'll add on the 32 to the other side, divide everything by 32. So if I first add on that 32, I get 30,032. And then if I divide everything by 32, we've got to that equation. So 3 over 2 all to the power of n. The worst part about this is because of that n. So to solve for that, what a lot of people tend to avoid, but what is definitely best to do with powers is just take logs of both sides. So you can use any log. I'd usually just go for the natural log because it's easier. And then with our log laws, because we'll have log of something to a power, we can bring that power down to the front. So I'd have n times, I'll write out log, but you can just use your natural log if you want. And then log on the other side, 30,000 and 32 divided by 32 is, I think, 938.5. And then we can just rearrange it then for n. So as long as you put these in both either to the same base in the logs or just use your natural log, this will always work. And from that, you should get about 16.88, somewhere around there. So n has to be greater than 16.88, but we wanted the least value for n. So the least integer value that n could be is 17. With a lot of these equations, you can always check it to make sure that you're doing it right. So if we wanted the sum of the first 17 terms, I've calculated this and we got 31,496.36. That was my sum of the first 17 terms. If I just calculate the sum of the first 16 terms, it's a lot lower, 20,986, somewhere around there. So when n is 17, that's our first value when the sum goes greater than 30,000. That was probably my worst question up to there. The next one that we have is more simultaneous equations with some different ways of solving them. So we have all the terms of a geometric series are positive. The sum of the first and second terms of the series is 10.8. So I'll write that in the equation first. So my first term and my second term sum up to 10.8. Next, the sum of the third and fourth terms of the series is 43.2. So the third term would be AR squared and the fourth term AR cubed, and they add up to 43.2. So we've got two equations, two unknowns, A and R, so we can always solve these with simultaneous equations. To make it a little bit easier, I'll just factor out an A in the first one, and I'll factorise the bottom one as well by AR squared. So there are loads of ways of doing these simultaneous equations. You can try a few ways. A lot of people like to rearrange this for A and then sub that back in. But what I do with this one, there are a few things that are quite similar in both equations. So if I've got A times 1 minus R, this equation here is just times by R squared. That's the only thing I missed out there. And that was 43.2. But I know a value for A times 1 minus R from my first equation. Oh, it's plus R, sorry. So if I sub in what I know already from A times 1 plus R, that's 10.8. I'll have 10.8 times R squared equals 43.2. And then we can just rearrange that for R squared, take the square root, and we've got our answer for R. That was the most work of it, and then we can just sub that back into any equation to find our value for A. I think from this one, R squared is 4. So then R would be plus or minus 2, but we know in this one all terms are positive. So it has to have a positive common ratio. So if I sub that back in, I'll go for my easy equation of A times 1 plus R. A times 1 plus when R is 2. And then we can rearrange that just to get a value of A is 3.6. So that's my first term and my common ratio for the series. These are usually always followed by find the sum of the first however many terms. So here we've just got find the sum of the first 16 terms. And then that's just subbing it into our formula. So A times 1 minus R to the power n to the power 16 all over 1 minus R, when my R is 2. and I'll let you work that one out. I think from that one, even though we start on 3.6, because the common ratio is 2, it's doubling every time, we get quite a high value. I think it's 235,926. That one. The next one that I wanted to do was just another algebraic one, but now in the form of a geometric series. So with our arithmetic one, we knew that the difference between them was the same. Now we want to look at the common ratio between them. So if the first term is k plus 10, the second term is k, and the third term is k minus 6, because we just want to find this constant k, the ratios between them must be the same. So it's times them by the same amount each time. So if I do k divided by k plus 10, that'll give me my common ratio. And also I could have done k minus 6 divided by k, my third term divided by my second term. That'd also be my common ratio. So we've just got a nice quadratic in k, which you can solve then. So you should get k squared is k minus 6 times k plus 10. That gives k squared plus 4k minus 60 on one side, k squared on the other. So then we have 4k minus 60 equals 0. Our k squareds will cancel out. And then we can solve that for k and get k is 15. The next one that we have for that is find the sum to infinity of the series. So if we have our sum to infinity formula, that was just a over 1 minus r, the nicer formula, because that r to the n would tend to 0. We just need to have a look at what our first term and common ratio is between them then. So if k is 15, my first term would be 25, my second term would just be 15, and my third term would be 9. So I know that is my first 3 terms. So a must be 25, and then the common ratio between them is either if I do 15 over 25 or 9 over 15. So that's times by 3/5 each time as it's getting smaller. So if I sub those into my formula, a is 25, r is 3/5. I think you get the value of 62.5 for that one for the sum to infinity. So these don't go too high if the value of r is less than 1. So our 25 is definitely our biggest term, 15, 9, it's going down by 3/5 each time. So there are a lot of the terms in that series are really, really small. The last part that I have here is 2 exam style questions. And I don't want to ruin the fun and just give you the answer to these. So I'm going to give you some hints and then let you work with them. But the full solutions to these will be uploaded as well.
Rianne, before you just go on to that last one, we've just had a question regarding the last question that you've done.
Yeah.
Saying, is there proof of this for the sum to infinity?
Okay. You wouldn't be asked to prove it. That would be mean. But if you wanted to, I will find it. Yeah. As n gets bigger and tends to infinity, that value of r to the n would tend to 0. So we'd have in our normal formula 1 minus r to the n over 1 minus r would just go to a times 1 minus 0 over 1 minus r. So that 1 minus 0 would just be 1, and we just have that a over 1 minus r. So that's the only way to kind of prove that limit. But for that one as well, you can check it and write out a few of the next terms. Because a lot of them, I think after like the 5th or 6th term, they go to less than 1. And then they don't have much effect when you're doing the sum to infinity of the whole series then, if that helps.
Oh, thanks, Rhiannon. Can everyone just put in if that helped, please, if that answered your question? Thank you.
Thanks for questions though. Please do ask if you get stuck on anything. The last part that I just want to give you some hints to do here is, some of you may recognise this question. It was, I'll see if I can remember, the 2018 EdExcel paper 2 A-level maths. I think it was question 4 on the paper, and I think it was worth 4 marks. Where a lot of people got stuck with this is they started to write out the series and realise it doesn't exactly go into the form of an arithmetic series or a geometric series. So that's where people just went, I don't know what to do, I can't do it. But you can split it up. So if we look separately at the sum of the first part, and then we'll consider that sum of the next part, 2 to the r. Then we'll look at them both separately. So you can see that 3 plus 5r, when r is 1, we'll get 8. When r is 2, we'll get 13. When r is 3, we'll get 18, and so on. You can see the first term, 8, and the common difference, d is 5 in that one. So you can put into your formula for your sum of the first 16 terms. And in this one, 2 to the r, first term is 2, then 4, and 8, 16, and this one's just going up in powers of 2. So then you can see the first term there is 2, the common ratio is 2 as well, and you can put that into your summation for the sum to n terms of your first 16 terms of your geometric series. So that's the hint with that one. And because it's a show that question, you'll know that you've got it right at the end as well. Another one that I wanted to just give you a hint for, another question that involves both arithmetic and geometric series, is this one. So 3 consecutive terms, we've done a few questions, consecutive terms, are a, b, and 3a plus 4. The first part's quite nice because it just finds an expression of b in terms of a. So if we looked at the difference between the third term and the second term, that's the same as the difference between the second term and the first term. That's really nice to just rearrange that for b equals something, and it'll be something in terms of a. So that's a nice mark. The final one that we have is, given also that a, b, and 6a plus 1 are consecutive terms of a geometric series, and a and b are integers, then we'll find the values of a and b as well. So for this one, with the geometric one, we'll have the ratios between them are the same. So that was that b over a. That second term over the first term will be the same ratio as the third term, 6a plus 1, over the second term, which is just b. If you rearrange that, the first part really helps there because you can sub in your value of b. You'll get a lovely quadratic in a, solve that for quadratic in a, and you'll get both values of A and B out. So I hope that one helps. And then all the full solutions to that one will be uploaded at the end. I'll leave that up there for a minute, but I will pass back over to Emma as well.
Oh, brilliant. I think that's been really useful for people. I will admit I'm rubbish at maths, so a lot of it did go over my head a little bit. But yeah, thank you so much. If anyone's got any questions, can you put them in the chat now before we finish, if that's okay? Just to let you know as well, we do have a series of these talks going on. So the next one will be on the 28th. Same time, same place. You just need to go onto the website again and just click the link, and that subject will be on circles, and it'll be Rhiannon again who will be helping you with that one. If you don't have any questions, it's been really, really lovely to meet you. If you can fill in the form that's been attached, just so we can carry on doing this type of work, really, if you found it useful, it'd be lovely if you could just pop your details in. It doesn't get shared with anyone other than on that HEAT database, which is just for us as a university. If you do want to take a look at any other events that we've got coming up, you can go to the outreach page on the University of Chester website, and you'll find all of our resources and information about all the next events, and again for that circles one and the other ones as well. So I'd like to say thank you to Rhiannon. I hope you've all managed to get a lot out of it. If you do have any queries in regards to what you've done today or any future events, then you can just email us at outreach@chester.ac.uk and we'll get those over to Rhiannon for you. So for now, I hope you all have a lovely evening. I hope your tea's ready for you now. And I'd like to say thanks to Rhiannon.
Thank you.
No problem. Thanks everyone, and we hope to see you again next week. Thanks.
Thank you.